right, I'm Russell Deitrick. I'm a student at University of Washington, also working with the VPL. I'm going to be shifting gears a little bit and talking about larger scale processes, in particular the triple star system of Alpha Cyn and Proxima. So in case you haven't heard, a planet was discovered orbiting Proxima Centauri, our nearest neighbor. All right, I'll move on. So one of the things that Tom Quinn, who's a professor at UW, pointed out right away was that Proxima is not alone. In this image, we can see Alpha Centauri A and B. Little Proxima is circled with that red circle there. It's barely visible in this image. Proxima is about 13,000 AU from Alpha Centauri A and B. For a long time, it was unsure whether it was gravitationally bound or not, although new evidence strongly suggests that it is gravitationally bound. We wanted to work from the assumption that it is gravitationally bound to Alpha Centauri A and B. And if we assume that, then one of the things that we have to consider is that the galactic environment actually affects its orbit. So in particular, this can cause close encounters, close approaches between Alpha Centauri and Proxima. And we wanted to see how this might be able to affect its planetary system. This was inspired by a study a few years back by Habitable. And they basically took the solar system gas giants and the sun and placed it in a wide binary system. And one of the things that they found is that these galactic forces that I haven't explained yet, but will in a moment, they actually drive the system to high eccentricity in many cases and cause disruption of the outer planets, which of course is catastrophic if you are concerned about your planetary system maintaining nice stable orbits. So the galactic forces that I'm referring to are two items, the galactic tides and stellar encounters. What I mean by that is stars that pass within a parsec or so of the system. Galactic tides are basically just this idea that it is denser close to the galactic midplane, and so at a given moment, the two stars may be different distances from the galactic midplane and be experiencing different gravitational forces. And so we can think of that as a tide, a differential force across the system. The other is forces from passing stars, which can impart or steal a little energy or angular momentum from the system. Another thing that I'm going to kind of gloss over here, but I'm happy to answer questions about, is this idea of radial migration, that stars don't necessarily have to stay where they formed. And we think for very good reasons that Proxima and Alpha Centauri did not form in their current location. So what does that actually look like? I should also mention that in this sort of proof of concept study, we were treating Alpha Centauri as a single mass rather than two bodies, just because of the difficulty of modeling the dynamics of those bodies, of the three-body dynamics. So we built a secular model for the galactic tides and the stellar encounters and looked at many different possible orbits that Proxima could have started with. Some of these configurations actually will go through having these close approaches. One I'm showing here, the distance on the right, basically this is the apastron, periastron, and semi-major axis, apastron, periastron of Proxima and Alpha Centauri A and B. As a function of time, this is billions of years. And then the eccentricity on the right, as you can see, it spends a lot of time at high eccentricity. The dashed line refers to time of radial migration when it moved from its formation location to its current location. But what you can see in this particular configuration is that they actually get within a few hundred AU of each other. Many of the simulations that we looked at actually do this. And if I actually build some histograms based on those simulations, what you can see here are I've taken the minimum pericenter location in all of these different configurations and bend them accordingly, according to their initial eccentricity, semi-major axis, and inclination. The black line here represents configurations that never had close approaches within 200 AU. Purple are simulations where they did approach within 200 AU, orange within 100, and red within 40. And noting that apocenter for alpha sin A and B is about 36 AU, this is actually, these configurations are actually probably destructive to the stellar system in addition to planetary systems. And so we're still trying to understand that, since we're still working on models of the three-body dynamics here. But again, just treating alpha sin as a point mass, we decided to run some in-body simulations to look at what a close passage does to a planetary system. And I've modeled several different flavors of planetary systems. One, of course, is just Proxima b, the planet that we know about. So one of the things we wanted to know, of course, is how does this close approach affect the planet that we know about, assuming that it's the only planet in the system. So I actually am showing here one simulation where Alpha Centauri and Proxima get within 40 AU of each other, and Proxima b starts with a relatively high eccentricity. And as you can see, there's not much happening with either the semi-major axis, apastron, or periastron. Or the eccentricity, we see a little pulse just as during the close encounter, the center of the mass of the system is shifting a little bit, but it quickly relaxes back to its original value. And so we would say that these close encounters are not going to have much of an impact on Proxima b if it's the only planet in the system. Now, just shifting to something analogous to what Cabedal did, I took solar system gas giants, placed them at their known locations around, instead of in the solar system around Proxima, and looked at what a close approach with Alpha Centauri does to that system. This is one where Alpha and Proxima get within 200 AU of each other. And as you can see, the distances of the planets, the apastron, semi-major axis, and periastron of Jupiter, Saturn, Uranus, and Neptune. This is the time of the close approach. After the close approach, Neptune and Uranus actually end up on crossing orbits. So this is something that is really bad for stability of the system. This is something where we would expect one of the planets to get ejected or some other devastating consequence after millions of years in the system. Yeah, so the point is, this is actually the best case scenario that I ran for this type of extended planetary system. In most of them, one of the planets, Uranus or Neptune, gets ejected almost immediately after the encounter. But what we'll argue based on this is that planets that are, if planets ever did exist far tens of AU from Proxima, this is bad news for them, these kinds of close approaches. So if it did ever have planetary systems like this, even smaller mass most likely, since gas giants are not as common around M dwarfs, and these close approaches occurred, then we would expect that that there wouldn't be this extended type of planetary system orbiting Proxima. But of course, this has the caveat that we didn't model the triple star dynamics because it's sufficiently complicated. This can actually modify the effects of close approaches. This is a test simulation by Nate Cabe showing what happens if you place a tertiary around an inner binary without resolving that inner binary. You can see that it gets within a few hundred AU, but if you actually resolve the effects of that inner binary, the faster precession rate actually shields the tertiary from these close approaches. And so this is something that we still need to consider. We're doing that in sort of a two-pronged approach. One is using our secular model and modeling the triple star dynamics as a quadrupole. This shows the effects of adding the quadrupole moment, where in red this is combining A and B, the inner binary, and then in blue, resolving their effects in a quadrupole moment. And then, of course, this secular approximation breaks down, so we will still need to resort to Nate Cabe's in-body approach where necessary. So we'll be using this to try to map out lots of different possible histories of the system of Alpha Centauri and Proxima Centauri. And with that, I will take any questions.
A few questions?
I answered them all, I guess.
Great talk.
Thanks.
So my mind was floating off to our solar system. What implications do you have for early evolution around the sun? Does it imply that maybe there was another star nearby from what you did?
For the sun, that's a great question. I'm not entirely sure how to answer that. Nate Cabe has written several papers on the motion of the sun moving through the galaxy. I think the implication is that the sun has been alone for a long time, considering that we have this extended system. Although I'm not sure that anyone has explored yet what effects that may, if the sun formed in a cluster and there were other stars that were close and the sun was later ejected, what effect that may have had on sort of the formation of the solar system. It's an interesting avenue to explore, for sure. Yeah.
Hi, this is Rene Heller.
Hi.
So given the orbital separation of, say, 13,000 AU between the AB binary and Proxima, that gives an orbital period of, say, 100,000 years, say 10 to the 5
It's about
years.
600,000. Is the latest result is about 600,000.
All right, so say it's
yeah.
10 to the 6 years. The system is 10 to the, 9 years old.
Yeah.
Gives 10 to the 3 orbits, so 1,000 orbits only, since the system has been existing. So
Right.
from the planetary regime, when we consider tides, we're talking about millions and hundreds of millions of years, or orbits.
Sure.
And so intuitively, I wouldn't guess that galactic tides haven't actually been effective over, say, 1,000 orbits of Proxima around the AB binary. So what's actually the effect of the galactic tides on the orbital evolution as part of your simulations?
Good question. So I'm sorry if that wasn't entirely clear. It's the galactic tides really aren't going to affect close things like the planets. The effect is that it affects it changes the shape of Proxima and Alpha Centauri's orbit. And so what happens is that over long time scales, you can have some of these close approaches. But you're right that there's not going to be very many orbits. There's 1,000-ish orbits, but it only takes a handful. It only takes a single close approach to disrupt an extended planetary system. Does that answer your question?
I was more wondering about the galactic tides. The tidal drag of the galactic midplane, as I understood, is what
Yes.
you include in your models. So over 1,000 orbits, I wouldn't expect the galactic midplane to have a significant effect of the orbital perturbation of Proxima around the binary, which is what I thought you would include in the model.
Oh, so the orbital effects of the inner binary are small at the distances that we're talking about of
I'll bug you.
thousands
I think I'll bug you on the coffee break again.
things. Okay, sorry, I'm not
No worries.
sure I understand
talk
what
to
you're
you.
asking. Yeah.
All right, let's thank Russell again.